CMOS logic and on the operation of a typical CMOS logic gate as the inverter, and we are going to make some considerations on the maximum operating clock frequency of digital logic and on power consumption, in order to clarify how trade-offs are established between power consumption, clock frequency, supply voltage, and so on. We are going to start from the basic CMOS logic gate, which is the Cmos inverter. As you know, the Cmos inverter is a very simple circuit, is the basic logic gate. It consists of a PMOS and of an NMOS, which have the drain in common, the gate in common, and the source of the NMOS is connected to ground, while the source of the PMOS is connected to VDD, to the supply voltage. So just to clarify, this is the gate of the NMOS and of the PMOS. These are the drains of the PMOS and of the NMOS, and these are the two source terminals. Okay, just we are now just we want to rehearse the operation of the NMOS. You know that the NMOS has three regions of operations. The first region of operation is when VGS is smaller than the threshold voltage of the NMOS, VTN, and in this condition the NMOS is off. Okay, just just let me put some notes. This is the threshold voltage of the NMOS. Okay, this N index means that we are discussing of a NMOS, and the T stays for threshold. Now we have other two regions of operations. The second region of operation is VGS larger than VTN, and VDS smaller than VGS minus VTN. You already know this region of operations from the basic course in electronics. I'm just want to start from here so that we can repeat some concepts. So in these conditions, we know that the device is on because the gate to source voltage is larger than the threshold voltage, so we have a channel below the gate dielectric, but VDS is small. In this situation we are in the so-called ohmic region. And actually, you know, the approximate expression of the drain current in the ohmic region is equal to a constant, which is a function of device materials and geometry, times VGS minus VTN. This quantity is called overdrive. The excess voltage on the gate with respect to the threshold voltage times VDS minus VDS squared over 2. Okay, just to mention a name, this voltage is called gate overdrive. So the overdrive is the gate voltage minus the threshold voltage. Okay, this is called ohmic region because the current is almost a linear function of the voltage between drain and source. The current which goes between drain and source is almost proportional to the voltage between drain and source. When I say almost, I mean that for small VDS we can neglect the term to the second power of VDS. This Kn is a function, as I said before, of material properties and of geometry. In detail, it is given by this expression, where W is the channel width, L is the channel length, mu n is the electron mobility, and C, Ox is the electric capacitance, gate dielectric capacitance per unit area. Nothing new here. Okay, these are already things that you know. Just to show you a simple schematic picture of the Mosfet, let's assume that this is the Mosfet okay. Seen partly from the top and partly in cross section. For example, here we have the source contact, here we have the drain contact, and this is the gate contact. This is the channel. We have electron flow from the source to the drain in this channel below the gate. And in this situation, this would be the channel length, this would be the channel width, and Cox is the capacitance per unit area of the gate dielectric. You see, this is a capacitor. You basically have a metal, an insulator, and a semiconductor below. Between the metal and the channel, the semiconductor channel, you have a dielectric. So basically you have a parallel plate capacitor. Okay, Cox is the capacitance of such capacitor per unit area, and as you know, the capacitance per unit area is the permittivity of the vacuum, epsilon 0, times the relative permittivity of the dielectric over the thickness of the oxide. So this is the oxide thickness. Just to stress the fact that this Kn is partly a function of materials and partly a function of geometry. Of course, W, L, and Tox are geometrical quantities, the width, the length, and the thickness of the oxide, whereas the electromobility is a property of silicon, the mobility of electrons in silicon, and the epsilon r is the relative permittivity of the material. In particular, it is the relative permittivity of the dielectric. Sorry. Okay. In addition to these two regions of operation, we have a third region of operation. So let me just add another page. The third region of operation is the situation in which we have VGS larger than VTN and also VDS larger than VGS minus VTN. The situation before was with the minus. Of course, with this third condition, we complete all the possibilities. This is called the saturation region. In this saturation region, we have a different expression for the drain current, which is given by this quantity. All the quantities have been already defined. We have 1/2 times this Kn times the overdrive to the square root. Okay. As you might recall, for analog applications, the saturation regions is the important region of operation, because in the saturation region the transistor behaves as an amplifier. Okay. Whereas for digital logic, the important regions of operations are the first two: the off region, in which the transistor behaves as a switch that is turned off, and the ohmic region, in which the transistor behaves essentially as a switch that is turned on, as a short circuit, more or less. Okay. Okay. This is what is important for the NMOS. For the PMOS, we have a similar situation, and of course we have let me just show you also the condition for the Pmos. The situation is very similar to the NMOS. The main difference is that the threshold voltage is smaller than 0, is negative, and that negative voltages have to be applied in order to turn on the device. Again, the regions of operations are the off region, when VGS is larger than VTP. So basically, you see we have changed sign. The off region for the NMOS was when VGS was smaller than VTN. Now the off region is when VGS is larger than VTP. Then we have the ohmic region, when VGS is smaller than VTP, and therefore just as a reminder, also smaller than 0, okay, and VDS is larger than VGS minus VTP. Consider that VGS minus VTP by definition is smaller than 0. VDS is larger than that, but it is still smaller than 0. Okay. By the way, this is something that I should remind you. If you look at the previous sketch, you can see that the source and the drain are identical. From a geometrical point of view, are exactly identical. We define, in the case of an NMOS, the source as the terminal with the lowest voltage, and in the case of a PMOS, the source is a terminal with a higher voltage. Okay, so by definition VDS has to be smaller than 0, because the source voltage is by definition larger than the drain voltage. So this is, let's say, by definition. This part. And then we in this situation, ID is equal to Kp times VGS minus VTP times VDS minus VDS squared over 2, which is identical to the expression that we had for the NMOS, except for the fact that we have different constant Kp and VTP. VTP is the threshold voltage of the PMOS. Kp is the transistor constant of the PMOS. So let me just mark this. This is the threshold voltage. And Kp is W over L times mu P times C ox, where mu P is the hole mobility, which means the mobility of holes, which are the charge carriers in a PMOS. Finally, we have the third situation, the saturation region. which is defined by VGS smaller than VTP again, and again VDS, which is negative, let's say 0 larger than VDS, larger no, VDS smaller than VGS minus VTP, and both of them are smaller than 0. In this situation, the current is equal to 1/2 times Kp times VGS minus VTP to the square root, to the square power. So this is just to recall the basic characteristics of the N MOSFET and of the P MOSFET that you already know, because I want to start from here and to work from here until we are able to explain the operation and the performance of CMOS logic gates and their power consumption. Now, what's the use of these expressions? When we know what are the voltages applied to the terminals, we know what is the region of operation, and then we are able to compute the current between drain and source. That's it. How do we use them? For example, we can evaluate the operation of the Cmos inverter with some detail. Let me redraw it here. This is the input, this is the output, so this is ground, which means then this is V in between the input and ground, and the output voltage is this V out. Of course, we know the current voltage characteristics of the PMOS and of the NMOS, and then we can compute the so-called transfer characteristics of the CMOS inverter. Let's do it. What is a transfer characteristic? Transfer characteristic is a curve. We have to plot the output voltage as a function of the input voltage. So we have V in on the x-axis, V out on the y-axis, and then of course we need to plot V out as a function of V in. V in can go from 0, which is the lowest voltage, the ground, to the supply voltage VDD. And as you can see, as you will see, basically also the output voltage will go from 0 to VDD. This is clearly the case because you see that in let's say DC conditions, constant current conditions, the output voltage is going to be between 0 and VDD. The current goes from VDD to 0. The voltage of this output terminal is going to be between the two extreme situations. Okay, what we can do now, we have to consider that when we apply a voltage on the at the input, we are basically biasing the two transistors in this way. This is the gate of both transistors. These are the sources of both transistors, and these are the two drains. So this means that V in is the VGS of the NMOS, and the VGS of the PMOS is V in minus VDD. Okay, so V in minus VDD is the VGS voltage of the PMOS. Regarding VDS, you can see here that Vout is the drain to source voltage of the NMOS. So Vout is the drain to source voltage of the NMOS, and Vout minus VDD is the drain to source voltage of the PMOS. Okay. So this means that when we choose a position on this XY axis, we have defined the operating point of both the NMOS and the PMOS. Okay, so for example, and this also means that we can, let's say, divide the whole space in different regions in which we can say what's the operating condition of the NMOS and what is the operating condition of the PMOS. For example, let's consider the NMOS first. The off condition is when VGS is smaller than VTN, but VGS is equal to V in. So when V in is smaller than VGS, V in is VGS. When V in is smaller than the threshold voltage of the NMOS is in the off state. This on the XY axis is a region of the plane, because for example this is VTN. V in smaller than VTN means this region, the region to the left of this vertical line. So in this region the N MOSFET is off. Okay. On the right of this axis, the N MOSFET can be in one of the other two operating conditions. For example, in the ohmic region, we have VGS, which is V in, larger than VTN, so we are on the left, but also we have an additional condition. If you remember, VDS must be smaller than VGS minus VT. This is something that we wrote in the previous sheet. VDS is equal to Vout, so Vout must be smaller than the overdrive, which is Vin minus Vtn. So what I'm doing now is simply I'm translating the conditions for the operating conditions in terms of the input and output voltages of the inverter. Also, these two expressions define a region in the xy axis. If you look here, Vin is larger than Vtn is on the right of this vertical line, but also we have Vout smaller than Vin minus Vtn. This is a line, and actually is a line which has a slope equal to 1, and it is 0, Vout is 0 when Vin is equal to Vtn. So this is a point through which the line passes, and the line has a slope equal to 1. Okay, so below, because we are taking the smaller side, below this line, the NMOS is in the ohmic region, and above this line there's no reason to do the rest of the calculation. Of course, the conditions completely divide the space in 3 regions. Above this line we will have the NMOS in saturation. So 1, 2, 3. Okay, we have completely divided the quadrant into 3 regions. Of course, we are not interested in the other 3 quadrants, because Vin and Vout are both between 0 and Vin, so they are both positive. Okay, we can repeat the same considerations for the PMOS. As I said before, with these considerations we are able to say for each point in this xy plane what is the operating condition of the NMOS and what is the operating condition of the PMOS. Okay, let's write the same considerations for the PMOS. Okay, we know that the PMOS is off if VGS-P is larger than VTP. Okay, but VGS-P, as I wrote here, is Vin minus VDD. So this means Vin minus VDD, okay, larger than VTP, which means Vin larger than VDD plus VTP. Okay, so for VTP is negative, as we have said before. So for example, this point is Vtn, is VDD plus VTP. This is VDD plus VTP. So Vin larger than this situation means that I must draw the line and take the larger side. So on the right I have that the PMOS is off. And then for the PMOS, let's draw the ohmic region conditions. Of course, we have a condition of VGS which is VGSP smaller than VTP, which means Vin smaller than VDD plus VTP. And then we have to add something. We need to in the ohmic region, you remember VDS P, this is the second condition, VDSP must be larger than VGSP minus VTP. But here VDSP is let me write completely. VDSP is V out minus VDD, as we wrote here. Larger than VGSP, which is V in minus VDD minus VTP. So you see, we can simplify here VDD and VDD. And then this becomes V out larger than V in minus VTP. Also in this case, this expression takes half a plane, which is delimited by a line that has a slope equal to 1, and that, for example, when V in is equal to 0, passes through V out equal to minus VTP. Okay, so for example, this is minus VTP, the line is this one. The upper side of this line, the larger side of this line, is the ohmic region. So here we have ohmic region, the Pmos in the ohmic region, and in this other region delimited by the remaining parts of the plane, so that there's no need to redo the complete calculation. In the remaining part of the plane, we have that the Pmos is in the saturation region. Okay, so we can do what we want now. If I take a point at random in this plane, for example here, I know that in this point the Pmos is in saturation region and the Nmos is also in saturation region. If I pick another place, I know exactly the situation. Okay, now why this is important? Because at this point I am able to compute the transfer characteristics. I know for any point the expression of the current for the Nmos and the current for the Pmos. Okay, I also know the that the current through the Nmos must be equal to the current through the Pmos, because the current is going along this direction. I can equate the two things, and from the knowledge of V in, always be able to compute V out. We can do it a little bit simpler and simply draw a qualitative line to, let's say, explain the operation of the inverter. For example, let's start from 0. Sorry. At 0, when V in is equal to 0, the Nmos is in the off region. Okay, and then if the Nmos is in the off region, the Pmos is for sure in conduction, because when Vin is equal to 0, the Pmos is either in the saturation region or in the ohmic region, okay, depending on the out. But of course, if the current cannot go through the NMOS, but the PMOS is conducting, the output voltage will go at the voltage of the supply voltage. So we are starting from here. Okay. Then from here, when we increase the input voltage, the NMOS remains in the off region, and therefore the output voltage remains at the voltage of the power supply. So we are in this situation up to this point, because I stop here because at this point we have a change in the operating condition of the NMOS. So the transfer characteristics has a segment which we call number 1, which goes in this direction. In the number 1 condition, the NMOS is off and the PMOS is in the ohmic region, and the output voltage is VDD. Then what happens here? When we increase the voltage above VTN, the NMOS starts conducting. Here the NMOS passes from the off situation to the saturation condition. So we have some current through the NMOS. Since we have some current through the NMOS, we have current also through the PMOS, because otherwise we do not have current through the PMOS. If we have current through the PMOS, we have a voltage drop between the source and the drain of the PMOS. And this means that the output voltage starts to drop with respect to the supply voltage. So we have at the beginning a small drop and then an increasing drop here. This is the second branch of the current voltage characteristic. Okay. Then I stop here because here something different happens. When we cross this line, the PMOS goes from the ohmic region to the saturation region. So from a qualitative point of view, nothing changes. Both the PMOS and the NMOS are conducting. They are crossed by current, and since I am from a qualitative point of view, what I can say is that since I am increasing Vin, I'm in, let's say, biasing in more in the conducting state the NMOS and less in the conducting state the PMOS. So the voltage drop on the PMOS is going to increase, and the voltage drop on the NMOS is going to be reduced, so that the out is going to go down. And actually what happens is that here the behavior of the curve is really steep. It goes very, very fast down to lower output voltages. We have a sort of quick transition in this situation. Actually, we can try to understand exactly what is going on here, because it is relatively easy to write an analytical expression of this line. In principle, it is possible for all the lines, but it's not, let's say, easy, because if you do what I said before, you equate the current in the PMOS and the current in the NMOS in order to compute the output voltage, sometimes you can find, let's say, a difficult expression to solve analytically. But in this region, in region number 3, it is particularly easy, and therefore we do it because we can use a small signal model. you remember in region 3 both the PMOS and the NMOS are in saturation, so we can use the small circuit model of the MOSFET. Okay, let's write some of the things that we have said. IV transfer characteristic, we have said line 1 PMOS is in the ohmic region, and the NMOS is off. Line number 2, the PMOS is still in the ohmic region, and the NMOS is in saturation. Branch 3, the PMOS is in the saturation region, and the NMOS is again in saturation. Okay, now in this situation we can use the small circuit model and compute the variation of the output voltage as a function of the variation of the input voltage. Let's do it. This is the input voltage. We have that the gate of the NMOS and the gate of the PMOS correspond to the same node. The source of the NMOS is connected to ground, but also for small signal, also the source of the PMOS is connected to ground, because it is at a constant voltage, which is the supply voltage VDD. Now here we have the drain, which is the output voltage. The drain of the PMOS is coincident to the drain of the NMOS. This is the output voltage between this line and this point. Okay, now if we draw the equivalent circuit of both transistors, between the drain and the source of the NMOS we have a current generator GMN times V in, because V in is VGS-N, and let me write it completely. This is going to be VGS-N, but is equal to GMN V in. I'm adding N as an additional index in order to specify that we are talking about the NMOS. And then in parallel to it we have a resistance R output N, the output resistance of the equivalent circuit of the NMOS. As far as the PMOS is concerned, we have between the drain of the PMOS and the source of the PMOS, we have a current generator GMP times VGSP, which again is equal to GMP times V in, and in parallel to it we have the output resistance ROP of the PMOS. So what you should be able to see here is that we can simplify this circuit, and basically we have that the two current generators are in parallel and the two output resistors are in parallel. So this behaves as a single output between the out and 0. We have a single current generator equal to GMN plus GMP V in, and the single resistor equal to RON in parallel to ROP. So this means that V out is equal to minus the drop on the output resistor is the current times the output resistor, so is equal to minus RON times ROP times GMN times plus GMP times V in. So V out over V in is given by that one. So this is the, we can call this expression minus A0, because this is a voltage gain of the inverter when both the PMOS and the NMOS are in the saturation region. And this is of course a small signal amplification, which is the slope of the curve in the region 3. So if we go back, the slope here is equal to minus A0, the quantity that we have computed. So this is just to show you that in this region the curve is basically a straight line with a slope equal to the amplification of the inverter when both the PMOS and the NMOS are in the saturation region. This number can be pretty high, which means that the line is almost vertical in this region. Okay, then here we have another change. When you cross this line, the NMOS goes from saturation to the ohmic region, and this means that the voltage drop on the NMOS starts to become very small, and in the end the line is going to degrade. The fourth branch is this one, and then in this situation the PMOS goes off, so we have no current anymore. The PMOS is interdicted, is an open circuit, therefore there's no current through the NMOS, which is conducting, and the output voltage goes to ground. So it is at 0. So this is the transfer characteristics of the Cmos inverter. It's really different from an ideal switch that we can imagine. The only situation in which the output is 0 or VDD are the branches 5 and 1, but between 5 and 1 the output voltage goes as a continuum from 0 to VDD. So just to complete this line, in the fourth branch, the PMOS is in saturation and the NMOS is in the ohmic region, and in the fifth branch the PMOS is off and the NMOS is in the ohmic region. Okay, let's go back here. One consideration that we should do now is this one. What is the almost ideal line that we would have as a transfer characteristic? The line that would give us the maximum noise margin for the high level and for the low level. I can draw it because it is relatively easy to think about. We would like something like this. The output voltage should be equal to VDD when the input voltage is between 0 and VDD half, and then the output voltage should abruptly go to 0 when the input voltage is between VDD half and VDD. So this would be the ideal characteristics. Of course, what we have is not an ideal line, but there are some situations that we would like to achieve. The first and easiest thing to achieve is the fact of having a symmetric characteristics, something that as is symmetric the ideal characteristics, something that, for example, passes through the input voltage VDD half and the output voltage VDD half, so that these two branches are more or less identical. So this, as you may imagine, is easily obtained if the characteristics of the PMOS and the characteristics of the NMOS are identical. Because if they are identical, these transfer characteristics must be symmetrical. There's no difference between the lower half and the upper half of the characteristics. We have a change of role between the PMOS and the NMOS, but the behavior of the curve is identical. If you remember the expressions that we have used for the PMOS and for the NMOS, look at the saturation region. For the ohmic region, the situation is the same. You can see that if Kn is equal to Kp and Vtn is equal to Vtp in absolute value, Vtp is negative, Vtn is positive, but if let's say Vtn is equal to minus Vtp, the IV characteristics of the NMOS and the IV characteristics of the PMOS are identical in saturation region. They are also identical in the ohmic region, and therefore it is easy to demonstrate that this transfer characteristics has this branch which is repeated symmetrically in the second half. Okay, so and this is a situation which we really want to have, and it's called a balanced inverter. And this is actually a design constraint for the inverter. In a balanced inverter, when V in is equal to VDD half, then V out is equal to VDD half. And it is true if the PMOS and NMOS characteristics are complementary. And this requires that Vtp is equal to minus Vtn and Kn is equal to Kp. This is obtained with doping. So is obtained with doping of a material. So it's a technological achievement that it is possible by treating appropriately the semiconducting material, the silicon used for the PMOS and for the NMOS. And Kn equal to Kp actually requires a geometrical constraint, because you remember that Kn is equal to W over L times mu times Cox. Let me add the N suffix in order to indicate that we're talking about the NMOS. and the PMOS is WP over LP times mu P times C ox. The oxide is the same for the PMOS and for the NMOS because they are fabricated at the same time, so we can discard these conditions. Mu N and mu P are two qualities of the electron and hole mobility, so are material properties. The length, the channel length, is typically the minimum achievable in the given technology. So it's not a design degree of freedom. In digital logic, one always chooses the minimum channel length because the minimum channel length corresponds to the maximum operating frequency and to the minimum power consumption. So it's important to keep the minimum length for the PMOS and for the NMOS. And so you see that from the design point of view, we need to choose a width for the channel of the NMOS and the width of the channel of the PMOS so that this condition is satisfied. So since the mobilities are typically different, we need to compensate for different mobility with different width of the P MOSFET and of the N MOSFET. Okay? In let's say traditional CMOS, we have standard silicon in which the mobility of electrons is almost twice the mobility of holes, and therefore in order to maintain this condition we need to have P MOSFET which are almost twice as large as the N MOSFET. Okay? This is what happens in traditional CMOS. For modern CMOS, we have materials engineering. You remember the thing that we discussed last week. Basically, we use strain for silicon in order to change the property of the material, and in particular to equalize the mobility of electrons and the mobility of holes. And in this case, we can have equal width for P MOSFET and for N MOSFET. Now, this is very important because for logic gates for inverters, one typically uses the minimum width for transistors. So if we can use the minimum width for the PMOS, it means that the whole inverter is much smaller. Because we, in any case, for the NMOS, we use the minimum width, which is typically twice the minimum length. And in modern CMOS, this means that we are able to build smaller inverters and, as a consequence, smaller logic gates. By virtue of this equalization of electron and holes mobilities, we are able to make smaller logic gates. Okay, I think we can make a break here.